Thanks a lot for this kind invitation. So I will talk in the next hour about the origin of cosmic rays. I just realized that normally I put my email address on the first slide. I forgot. So in case you want to contact me after the
Yeah.
lecture to ask questions, you can ask my email address to Kamel, and he can share it with you.
Yeah.
Okay, so to talk about cosmic rays, but first of all, I want to disclose that I am not an expert in machine learning or artificial intelligence, but in recent years, I did this simple exercise. I counted the number of papers published as a function of years that contain in the abstract the word machine learning at cosmic rays, and you see that, boom, there was an explosion. And the same holds for cosmic rays and deep learning. So these techniques now are used massively in the field of cosmic rays. So I think that to have an introduction on the physics of cosmic rays could be useful for some of you that maybe in the future will be inspired to apply techniques of machine learning to cosmic ray physics. So let's start with the history of cosmic rays. So the history of cosmic rays started long ago with a very simple instrument, the electroscope, which is an extremely simple instrument. So basically you detect electric charge. You have a metal rod inside an insulator, and if you get a charged body close to the rod gets charged. And at the end of the rod, there are two golden leaves that they get also charged of the same charge, and so they repel. And the repulsion of these indicates electric charge. So okay, this is just the same. So basically, in 1785, Coulomb noted that when he charged an electroscope, this is an old electroscope. You see the two golden leaves here, they were diverging because the rod was charged. He noted that if he left the electroscope in the lab, after some time, the electroscope discharged spontaneously. And then Faraday, a bit later, he improved the insulation system of the electroscope because he thought it could be simply an instrumental problem. But in fact, he found that it was not an instrumental problem, but the electroscope was discharging spontaneously. Then Crookes, in 1879, Crookes did experiments and he tried to change the air inside this insulated box. And he saw that the time needed to discharge the electroscope depended on the pressure of the air. And so he concluded that the discharge was due to the fact that the air inside the electroscope was ionized. But then the point was who ionizes the air. And then in 1895, Becquerel discovered radioactivity, and then people thought they had a solution to this problem because they said, okay, if I have an electroscope which is charged, and I have a radioactive source emits energetic particles can ionize the air, and so if you have an electroscope which is charged plus, the electrons that you generate in this ionization, that they can go to the electroscope and discharge it. And then, of course, the air inside the electroscope remains positively charged. Okay, and then, so the idea was that as the Earth contains radioactive isotopes, and so we are constantly bombarded from the ground by ionizing radiation. People thought that this was the solution of the problem. And then, if this is the solution of the problem, then of course, if you take your electroscope and you bring it away from the Earth, then the effect should be slower. Electroscopes should discharge more slowly. And then a priest, Father Theodor Wolff, went on the Eiffel Tower. He brought electroscopes on the top of the Eiffel Tower, and then he measured how long it took to discharge them, and then he did the same at the base of the Eiffel Tower. And yet here is the table from his paper, which is 1910 or 11, I think. And in fact, data were not very clear, but then he concluded that he found an effect which was much smaller than what he expected. But he said, well, I don't have any other plausible explanation of the spontaneous discharge of electroscope. And so I conclude that it must be radioactivity from the ground. Then there was another guy, this time in Italy, Pacini, who in 1911 he did something, he did the opposite. Instead of bringing the electroscopes up, he brought them down. He put electroscope underwater. He went on the coast of Livorno, which is a city in Italy, and he put electroscope underwater. And he saw that if he put electroscope underwater, these electroscopes were discharging faster. And so he said that they were discharging faster because the water above the electroscope was screening the radiation. And so he understood, and this was extremely important, he understood that the radiation that ionizes the air inside the electroscopes comes from up, not from down. And so he said it comes from up from the atmosphere. And then in 1912, Victor S. was even more extreme. He took a balloon, and with a balloon he flew up to more than 5 kilometers. And here is the plot by Hess, and this basically this plot as a function of the altitude, it measures how many ionization you produce in the electroscope, and you see that the effect increases with height. And you see that at the beginning there is a small drop, and this is what the guy on the top of the Tour Eiffel was observing. So basically there is an initial drop because there is some radioactivity from the ground. But then some other component emerges, and the electroscope ionizes faster and faster if you go up. And so as concluded, and then other people did experiments at even larger heights, he concluded that this radiation comes from outside of the atmosphere, comes from space. And this is the discovery of cosmic rays. And in fact, S got a Nobel Prize, I think, in the 30s for this discovery. So the Earth is constantly bombarded by a flux of energetic particles coming from space. Okay, so what are they? Here I copied the first paragraph of a very nice book of cosmic rays by Tom Geiser. And basically, cosmic rays are mainly protons, are atomic nuclei, but mainly protons. 90% of them are protons, and they hit the atmosphere at a very large rate. Each square meter is bombarded by 1,000 particles per second. And these particles are relativistic, so they move at a velocity which is very close to the speed of light. And we, cosmic ray physicists, what we want to do is to understand where they are from and how they are accelerated to these very high energies. So if you measure, this is the energy of the cosmic ray particles. If you measure the flux that at the top of the atmosphere of these particles, because the atmosphere attenuates, of course, a lot these fluxes, which is good for our health. So if you measure the spectrum of these particles as a function of their energy, you see that the three colors here refers to different times of observation. So you see that at high energies, the flux of cosmic rays is very stable in time. So you have a very uniform flux of particles hitting the Earth. If you go to energy below, let's say 10 GeV, you see that the flux changes with time. And this changes in phase with solar activity. When the sun is more active, the cosmic rays have a minimum. And when the sun is less active, the cosmic rays have a maximum. And this, in fact, tells us that the sun being active, it means that the sun blows a wind of magnetized plasma, and this wind prevents cosmic rays of low energy to penetrate into the solar system and reach the Earth. And so basically, this suppression is not due to the fact that the intrinsic spectrum of cosmic rays bends, but is the fact that the sun prevents low energy particles to reach us. So the real spectrum will be something like this black line, but if we are near Earth, we don't know this spectrum. Okay. So basically what we see at low energies is impacted by the presence of the sun. Is not the spectrum of cosmic rays in the interstellar space, far away from the solar system. Okay, and there is something which is a bit problematic here, because if you see here is a log plot, so this is a power law, so the number of cosmic rays of energy E decreases with the energy to like e to the minus 2.7. 2.7 is very steep, which means that, let's say that we say, okay, here is the sun is impacting the spectrum. Let's assume that the spectrum simply continues as a power law to indefinitely small energies. If you do this and you calculate which is the total energy carried by these cosmic rays, so you integrate the number of particles times their energy over the entire range, you see that if you go to small minimum energy, so if you extrapolate a lot, this energetics explodes. So physics tells us that at some point, the intrinsic spectrum of cosmic rays should drop. Otherwise, energetics explodes. Very good. So how do we check if this happens or not? Well, long ago, in 1977, I was almost 1 year old. The two Voyager probes, Voyager 1 and Voyager 2, were launched. And these probes carried on board two cosmic ray detectors. And what is amazing about Voyager 1 and 2 is that they are still running. I mean, now they are here. And you see, here is the solar system. Here is the solar wind termination shock. And this is the wind that prevents cosmic rays to penetrate the solar system. And then here you have a bow shock because the sun moves with respect to the interstellar medium. And so here basically is another shock, which is the bow shock that separates the shocked wind material to the interstellar medium. And you see that now Voyager 1 and 2 are outside of the region which is affected by the presence of the sun. And so now their cosmic ray detectors measure the real spectrum of cosmic rays in intergalactic space. And this is amazing. This is one of my favorite plots ever on cosmic rays, because you see, this is the year, and here is the count of cosmic ray particle in Voyager 1 as a function of time. And so you have to imagine that if you go on in time, Voyager 1 was getting farther and farther away from the Earth. And you see that at the beginning, the cosmic ray counts were going up and down, a lot of variation, and this was connected to variation in the solar activity. And you see that there is a period here. It's a bit periodic, and the period is 11 years. And 11 years is exactly the period which we know the solar activity has. And you see that the more the probe goes away from the Earth, you still see this period, but it gets less and less pronounced because you are moving away and away from the sun. And so the effect on the sun of cosmic particles is smaller. And then you see that at some point you don't see it anymore. The flux of cosmic rays increases. And here you have a very, very different behavior. Because after 2012, if you zoom in here, you see that here we are zooming. So you see that the count rates become extremely stable, which means that basically in this point, the probe crossed the heliopause, which is the surface that separates the solar wind to the interstellar material, and now it's measuring the real spectrum of cosmic rays in interstellar space. So basically, these white dots now, which are extremely stable in time, are the measurement of the two Voyagers, and you see that the spectrum of cosmic rays indeed bends at low energies. Very good. And then, of course, Voyager measured also helium, lithium, beryllium, boron, all the elements in the cosmic ray spectrum. You see that you always have this trend, this drop in the spectrum. And then, of course, you measure also electrons. Okay, but this is just to show you that all elements and all particles are measured by these detectors. Now, if we do this exercise, we take the spectrum of proton, helium, and electrons, which are the most abundant species in cosmic rays, and we compute two quantities of this spectrum. We measure the flux of particles and the energy carried by these particles. And you see that the flux of particles is for nuclei is dominated by sub-GeV particles. From electrons, we don't know where it is dominated because we don't have measurement below this. Why the energy distribution of these particles is always dominated by, let's say, GeV particles. So it means that now that we have this measurement by Voyager and we know where the spectrum bends, we control the total energetics of cosmic rays. So we know how much energy we have near Earth in cosmic rays. And this energy, the energy density of cosmic rays just outside of the solar system, of the solar wind, is 1 electron volt per cubic centimeter. And this amount of energy is large because, I mean, if you are not familiar with the astrophysics of the Milky Way, 1 electron volt per cubic centimeter is also the energy density of the interstellar gas, the thermal energy density of the interstellar gas, and is also the energy density of the interstellar magnetic field. So you have to imagine that in our galaxy, the energy is shared equally between normal gas, magnetic field, and cosmic rays. So cosmic rays are very important in the evolution and in the behavior of the interstellar medium and of our galaxy. Okay, so now the question is, we measure cosmic rays at the top of the atmosphere or with the Voyagers just outside of the solar wind. But we do not have, of course, for obvious reasons, measurements in other locations in the universe because we cannot send probes. I mean, the Voyager is the object built by man, which is at the largest distance from Earth. So the question that arises is, cosmic rays are a local phenomenon or a global phenomenon? And we can imagine, so first of all, we can do this. The bombardment of cosmic ray at the Earth impacts geological and biological material. So people studying rocks and biological samples, they can infer from some basically from some radioactive isotopes that are generated in the bombardment of cosmic rays. They can infer that the flux of cosmic rays had to be stable of the past billion years. Now, in 1 billion years, the sun performs several revolutions around the galactic center because the galaxy rotates, no? And so it means that the cosmic ray flux must be also constant along the orbit of the sun, which is doing, in 1 billion years, the sun does 5 orbits around the galactic center. So cosmic rays are probably stable in time and space. And in fact, another observable, which is very interesting, is the anisotropy of these particles. So basically, this map tells you how many cosmic rays we get from each direction in the sky. And you see that if you look the color, it looks like there are less cosmic rays from this region of the sky, more from this region, and a bit less from here. But now look the scale. This is the anisotropy, but it is in unit of 10 to minus 3. So it means that these differences are tiny. So it means that the flux of cosmic rays is very isotropic. So basically, any direction, from any direction in the sky, we see a very similar flux of cosmic particles. Okay, so basically, from this data, we can imagine 3 scenarios. One scenario where cosmic rays are very local. Let's say they are connected to something going on very close to the sun. And so they occupy only a region close to us. Then another scenario is cosmic rays are galactic, so they occupy only the volume of the galaxy. And the third scenario is cosmic rays are cosmological, so the entire universe is filled with cosmic rays. And a priori, I mean, at this point of the discussion, we could accept all these scenarios. Okay, the cosmological origin of cosmic rays in the early days of cosmic ray studies was the favorite one because the isotropy of cosmic rays, so the fact that from any direction in the sky you see the same amount of cosmic rays, fits very well with the cosmological origin, because if cosmic rays are everywhere, well, then you get the same amount of them from each direction. But in fact, you have to be careful here because there are magnetic fields. And so magnetic fields can deflect charged particles, and cosmic rays are charged particles. And so even in these two scenarios, you could imagine to have a very isotropic flux of particles if magnetic field completely isotropize the trajectory of cosmic rays. Okay, so let's see how to decide which of these scenarios is the best one. And then we go to the 50s, and this guy, Hayakawa, had an idea, which is quite smart. He said, okay, we know that close to the Earth, we have this amount of cosmic rays. This is the measured cosmic rays at the Earth. Then we know that the galaxy is done like this. So the galaxy is a disk which rotates, and the sun is quite at the edge of this disk, and then you have a bulge, so on. And then the disk is full of what we call interstellar medium, so gas, diffuse gas. And then you have a halo here, which is basically magnetized, so there is a magnetic field, but the density of the gas is very, very, very small. So basically, all the gas is concentrated in the disk. And so Ayakawa said, if cosmic rays are a local phenomenon, so are concentrated only along the sun, their interaction with the interstellar matter will produce neutral pions. So this is a proton in the cosmic rays that interact with the proton in the interstellar medium. You generate a neutral pion. Neutral pion decays into gamma rays, and gamma rays can be detected by telescopes. And you should note that in 52, there were no gamma ray telescope existing because you do gamma rays of GV, TV energies. And so Ayakawa was just saying, if one day we will have this telescope, we will be able to see this radiation. And the idea is the following. Now we have these telescopes, and you see that if you look at the sky in gamma rays, you see very clearly an excess of emission from the galactic disk. So it means that cosmic rays are not local, but are everywhere in the disk. And so basically, this rules out this hypothesis, okay? Both these hypotheses are still alive because, well, if you have cosmic rays filling these volumes and you have the gas only in the disk, you can have the interactions between cosmic rays and matter only in the disk, and so both the scenario reproduces the gamma ray observations. So how do we distinguish? We have outside of our galaxy, we have other galaxies. For example, at about 50 kiloparsec from the galaxy, so quite close. So the galaxy has a radius of 30 kiloparsec. We have a galaxy called the Small Magellanic Cloud. And we know astronomers are able to measure how much gas is contained in the Small Magellanic Cloud. So if we assume that cosmic rays are cosmological, so basically that they fill the entire universe with the same intensity, then if we know how much gas we have, we know how many interactions we have between cosmic rays and matter, and so we can predict the gamma ray emission from the Small Magellanic Cloud, from this external galaxy. And so this can be done, and now we know that now we can observe, now that we have telescope, we can observe this galaxy, and in fact, the gamma ray emission from this galaxy is about 10 times smaller than what we would expect if cosmic rays were everywhere in the universe, which means that the cosmic rays that in our galaxy are more, the density of cosmic rays is larger than the cosmic rays here. So cosmic rays are not cosmological. Their intensity is not constant in the entire universe. And so we are left with the galactic scenario. Cosmic rays are galactic. They are contained within our galaxy. Okay, in fact, not all cosmic rays are galactic, but most of them, because I told you that we have the disk in the galaxy with a lot of gas, and then we have a region called halo, which is a magnetized region with very little gas, but with a magnetic field. And this halo has some size. And so basically, cosmic rays are charged particles, so they, in a magnetic field, they gyrate, they perform a helical trajectory with radius r, which is the Larmor radius. And so you see that, and this increases with particle energy. So when the Larmor radius is larger than the size of your confining region, then cosmic rays cannot be confined in the galaxy. So it means that we can impose this equality, and we can see that cosmic rays below, let's say 10 to 18 electron volt can be confined in the galaxy. And so you see that basically all these guys are galactic, Then here we have a region where we don't know because it's a bit in between, and only these few guys here at extremely high energy are probably of extragalactic origin. So you see that most of the cosmic rays are galactic. They come from our galaxy. Okay. Now, another interesting thing that you can do with cosmic rays is to measure their composition. And here is the composition of cosmic rays. So you see, this is the atomic number. So cosmic rays are energetic nuclei. So they are defined by an atomic number. And here is the abundance of these particles that we observe. And in green, you have cosmic rays. And in black, you have the abundance that we have in the solar system, in the Earth, I mean, the normal, what we call the cosmic abundances. And you see that there is some rough agreement with some very big exceptions. Lithium, beryllium, boron are like beryllium is like 1 million times more abundant in cosmic rays than in ordinary matter. And also elements just below iron are a factor of, let's say, 1,000 overabundant in cosmic rays. So this is a huge difference. It's not a small one. Then if you remove these big differences, so you basically you remove these elements that don't fit with our solar composition, and you plot now the ratio between how many nuclei of a given atomic number, so this is hydrogen, helium, and blah blah, with respect to the cosmic abundances, you see that is not a flat line. So if you add cosmic rays with exactly the solar composition, you would expect a flat line, but you see that there are basically kind of two categories of elements, and these are different categories of elements because these elements are what we call volatiles, and these elements are what we call refractories. Now, volatiles are elements that in the interstellar matter are found in gas phase, so they are in gas. Refractories are elements that in the interstellar matter are mostly found in dust grains. So this tells us that the composition of cosmic rays, if we want to explain it, it needs dust. So dust particles may provide a source of cosmic rays because these refractories are more abundant in cosmic rays rather than in normal ordinary matter. And so dust grains must play a role. Okay. And then also you can also do isotopic composition measurements. So for example, here it is shown the ratio between the neon 22 and neon 20, and you see that in meteorites or local interstellar medium, this ratio is 0.1. In cosmic rays is 0.4. You see, if you look the details of the composition of cosmic rays, this composition is different than the normal cosmic composition. And this, in fact, tells us another important thing, that neon 22 is overabundant in cosmic rays, and we know that there are some stars, which we call Wolf-Rayet stars, that are characterized by winds, like the solar wind, no? Which are characterized by an overabundance of some element, and including neon 22. So this, you see that the observation of the composition of cosmic rays tells us many things. It tells us, in this case, that the stellar winds must play a role in the production of cosmic rays. Otherwise, we would not explain this excess of neon 22 in cosmic rays. Now, let's do a summary of the observations. What we learned from all the data that I just reviewed. So we learned that the intensity of cosmic rays is very stable in time. They are distributed homogeneously in the galaxy. They are galactic. They are isotropic, and so the magnetic field must deflect their trajectory a lot because we see a large degree of isotropy. They carry a lot of energy because we saw that the energy they carry is an important component of the interstellar medium. And then we know that in explaining their origin, dust, interstellar dust must play a role, and also stellar winds must play a role. Okay, good. Now I want to do some more technical physics and answer one question. How long do cosmic rays stay within the Milky Way? So you have to imagine that they will be accelerated somewhere and somehow, we don't know still how and where, And then they will travel in the magnetic field of the galaxy, and then at some point they may escape the galaxy. And in order to estimate how long it takes to escape, we have to go back to abundances and look at these huge discrepancies between the abundance in the solar system and the abundances in cosmic rays. So how do we explain this difference? This difference is explained in terms of spallation. Spallation happens when you have an energetic nucleus that impacts on a target, on another nucleus at rest. In this collision, you can fragment nuclei. And so, for example, you can imagine to have a cosmic ray carbon that is very energetic, and this carbon hits hydrogen, for example, in the interstellar medium. It fragments, and if you fragment carbon, you may generate lithium, beryllium, or boron, plus hydrogen or helium or whatever. So this is the way in which you generate these cosmic rays. You fragment heavier nuclei in collision with matter, with interstellar matter. Okay. And here, of course, we know the cross sections of these collisions. So this is cross section, for example, for protons with carbon. And you know that you can produce beryllium 11, lithium 7, lithium 6, beryllium 9, and so on. Very good. So now let's do this. Let's take the spectra of cosmic rays. Now, this is the energy of the particle, and this is the how many of these particles we observe. And we divide it by species, so hydrogen, helium, lithium, beryllium, boron, carbon, neon, oxygen, and so on. Now, hydrogen, then we ignore this low energy part because this bending is what I told you at the beginning, is the effect of sun, so we don't care about this. So let's look only from 10 GeV on. Look, hydrogen, helium, carbon, and oxygen are quite flat in this representation. Here I multiplied the spectrum by energy to the 2.7 to make it flat. So these are flat. Lithium, beryllium, boron are steeper. The spectrum drops. No? And nitrogen it drops, but less than lithium, beryllium, boron. Okay, now, how do we explain these differences? Knowing that spallation plays a role. Well, we do the hypothesis that the elements which have a flat spectrum are primaries. And primaries, I mean here, elements which are accelerated out of interstellar matter. So you take interstellar matter, you accelerate it, and you produce cosmic rays. Elements with a steep spectrum, we call them secondaries. So these elements are produced they are not accelerated, in fact, but they are the result of the spallation, for example, of carbon or oxygen, and that interact with interstellar matter, and it produces them. So they are not accelerated. They are simply produced in collision of energetic carbon or oxygen. And what about nitrogen? Nitrogen is the spectrum drops, but less steeply. And so we do the hypothesis that nitrogen is mixed. Part of nitrogen is of primary origin, and part is secondary. Okay, so now let's do something simple. Let's take boron. So boron in cosmic rays is much more abundant than boron in the interstellar medium. And let's assume that all this boron is produced by spallation of carbon and oxygen. Why only carbon and oxygen? Well, because they are the most abundant element in cosmic rays, heavier than boron. So you see all these elements are less abundant, and nitrogen also, you see there is a drop here, so it's smaller. So we take only carbon and oxygen. And then we say, okay, how much boron we produce in the interaction of carbon and oxygen. So we have to take the density of carbon and oxygen, multiply them by the cross-section, which is the probability to have a collision with matter that generates boron. And then we have to multiply by the velocity of the cosmic ray particles and by the density of the target of the interstellar medium. This tells you how much boron you produce per, let's say, cubic centimeter in interstellar space. Okay, and now there is some kind of a miracle here. Look, the carbon and the oxygen. Look, the x-axis and the y-axis. They are basically identical, the two spectra. You see, is between one, it is a bit less than 100, and there is the same. So if you overlap these two spectra, they are almost the same. And so we can simplify this by saying that the spectrum of oxygen is equal to the spectrum of carbon. And so you simplify this expression like this. Very good. At this point, that we know how much boron we produce, we should ask ourselves how boron is destroyed, for example, or lost. There are two possibilities. One possibility is that boron escapes our system after a time tau interstellar medium. And the other possibility is that boron also undergoes spallation. So boron has a collision with hydrogen in the interstellar medium and transforms in a lighter element. And so we lose boron. So basically we can, in steady state, we can balance the production rate of boron with the rate of destruction of boron, which is two components. One is escape from the galaxy and one is destruction due to collisions. Okay, so now there is something a bit weird that cosmic ray physicists do not like to use times, but they like to use what we call grammage. Grammage is, it has units of grams per square centimeter and represent the amount of interstellar matter which is crossed by cosmic rays in a given time. Okay, so basically we convert a time, we multiply it by the velocity of the particle, and this gives us the path length, and then we multiply by the mass density, and this gives a grams per square centimeter. Is how much matter is seen by a cosmic rays after a time tau. Okay, very good. And so we can also define both the grammage, so the grammage that cosmic rays has to experience in order to escape the galaxy, and also the grammage the cosmic ray have to experience, the boron has to experience to be destroyed by spallation. So now our equation where we equate the creation of boron and the destruction of boron can be written explicitly. This we derived a few slides ago. And then we do some simple manipulations and we substitute times with grammages and we obtain this very famous expression. Now, forget about the mathematical details, which are simple. This expression is an expression for the ratio between boron and carbon in cosmic rays. What do we have on the right-hand side of this equation? We have cross-sections, and cross-sections, we know them. They are measured with accelerators. Then we have the mass of the protons that we know, and then we have the grammage of boron that we know because the grammage of boron depends only on the spallation cross-section of boron to be destroyed. And so you see that if you measure this ratio, you are measuring the amount of matter that cosmic rays need to cross before escaping the galaxy. So we are measuring the escape time of cosmic rays from the galaxy. And the boron over carbon ratio is measured as a function of energy for cosmic rays by Voyager and by another instrument, which is called IMS2, for example. And you see that this here, boron over carbon, drops with energy. Now, this we don't understand, so let's not talk about this. But at high energy, we understand, and it drops with energy, which means that cosmic rays of larger energies have a smaller grammage, meaning that they cross less matter before escaping. And so basically it means that high energy particles escape faster from the galaxy than low energy particles. Okay, very good. Now, high energy particle escape faster, but then we have to and there is a subtlety here because you remember that the galaxy is a disk plus an halo, and you have a lot of mass, a lot of gas in the disk, and almost no gas in the halo. So how do we accumulate this grammage? There are two possibilities. One is this, so that the cosmic rays stay inside the galactic disk and they accumulate this grammage, and then at some point they escape the galaxy. Another scenario is that cosmic rays do this. So they can they are confined in a larger region, which is the magnetized halo, and then they can cross many times the disk, and they accumulate the grammage. So if we measure only the boron-over-carbon rate, we cannot distinguish between these two scenarios, because when a cosmic rays are here in the halo, they spend time in the galaxy, but they do not accumulate grammage because there is no gas here. Okay. Okay, very good. So how do we do to distinguish between those two scenarios? Because you see that in this case, the cosmic ray, the time that cosmic rays spend inside the galaxy could be much larger than this, because cosmic ray can spend a long time in the halo without accumulating grammage. How do we distinguish between these two? In order to distinguish between these two, we need a clock. We need something that is able to measure not the grammage, but time. And what do? We take short-lived radionuclides. So there are some isotopes that are radioactively unstable, and so after some time they decay, and so they are lost. And one of them is beryllium-10. And beryllium-10 basically has a decay time of about 1 million years. So let's go back to our grammage. So we saw that at 10 GeV, if you remember from this plot here, the boron-over-carbon can be converted into the grammage by means of this expression. You can do it. This is all analytic. You can do it with a pen. It's very nice. So at 10 GeV, the grammage, so the amount of matter traversed by cosmic rays is 7 grams per square centimeter. As we know the density of the interstellar medium, we can convert this grammage in the time that cosmic rays spend in the interstellar medium, which is a few million years. Now, if you take now a nucleus which is radioactive, but it has a decay time which is much longer than this, well, then you expect this guy to behave exactly as a stable isotope, and so it's useless. So what we need is an isotope which has a decay time which is similar to these numbers. And so beryllium-10 is ideal because it is a couple of mega years, so it's similar to this. And so it's a perfect clock. So now, how do we use beryllium-10 as a clock? We measure this ratio, how many cosmic rays we have of beryllium-10 over beryllium-9, because beryllium-9 is a stable element. So basically, the observed ratio of beryllium-10 and 9 will be equal to their ratio at production, and you remember that they are produced in spallation. They are producing cosmic ray collision, lithium, beryllium, boron. And so this ratio we know. And then is proportional to the time, to the decay time. This is the Lorentz factor of the particle, because for radiative particles, for relativistic particles, you have to time the relativistic effect of time dilation. But okay, let's ignore this. But is the time it takes to beryllium-10 to decay, while the beryllium-9 you have to multiply by the time it stays in the galaxy. So you see that basically you can measure everything here except of this, and so you can invert the expression and derive the escape time of cosmic rays from the galaxy. And if you do it, you put number from, you see, the ratio beryllium-10, beryllium-9 is measured here, the yellow dots. And if you put all numbers in, you see that you obtain an escape time of 50 million years versus the 4 million years that you got from the boron-over-carbon. And the fact that these two numbers are very different, it tells you that the solution is this. So cosmic rays are confined for 50 million years in the galaxy, but then when they are in the halo, they do not interact much with matter. They don't accumulate grammage, but they do when they cross the disk. And so you have to imagine that cosmic rays cross many times the disk, and they stay overall 50 million years in the galaxy, but only 4 million years in the disk. And this explains everything. So now I have to skip a lot of stuff because time here is running fast. I just want to go to the solution of our problem. So remember, the question is still, where are cosmic rays from? And the first guy who got it right, let's say, is Fritz Zwicky, which is this guy who has a very bad character, as you can see from this picture. And in fact, he was the first guy who proposed that cosmic rays come from supernova. In fact, this paper was written in 1934, and the paper was completely wrong because you see, the first sentence was cosmic rays are extragalactic, and we know now that they are galactic. But Zwicky was a very smart guy. He understood that in order to explain very energetic particles, you need extreme sources. You need sources that are able to release a lot of energy. And that's why he thought about supernovae. Now, why supernovae can accelerate cosmic rays? The main reason why we believe so is that we know that we have in our galaxy about 3 supernovae every century exploding. And we also know that each one of these supernovae is basically an explosion that releases mechanical energy, kinetic energy. And each supernova releases about 10 to 51 ergs of energy. So you can simply multiply these two numbers, the energy of one explosion and the rate of the explosion, and you get a power, an energy per unit time. So supernovae inject in the Milky Way 10 to 42 ergs per second of mechanical energy. But now you remember that we measure locally the energy density of cosmic rays. You remember we measure 1 electron volt per cubic centimeter. Then we know from gamma ray observation that these cosmic rays fill the entire galaxy. So you can say inside the disk of the galaxy, we will have this amount of energy, the energy density of cosmic rays times the volume of the disk. But then we also estimated how much time cosmic rays spend in the disk. So if we divide this by this time, we get also a power. And this is the power that you need to explain cosmic rays. And then you can notice that 10 to 41 is 10 times smaller than 10 to 42. So if supernova explosion are able to convert 10% of their energy into cosmic rays, then you can explain these particles. And this is still today, this is a very, very old argument, but it is still today the main argument that makes us think that cosmic rays come from supernovae. Very good. So now to conclude, I want to show you that every time you do an hypothesis, you have to test it. And to test this hypothesis, again, people went to gamma ray astronomy. And they said, okay, each supernova releases, in the explosion, releases 10 to 51 ergs of energy. If you want to explain cosmic rays, you need 10% of this energy, so 10 to 50 ergs, to be converted into cosmic rays. Then we know that these supernovae are exploding in the interstellar medium, so this gas that is everywhere in the disk, and we know the density of this gas. It's only 1 particle per cubic centimeter. And so these cosmic rays, accelerated as supernova remnants, can interact with this matter, produce neutral pions, and do gamma rays. And so people said, okay, if cosmic rays are accelerated in supernova remnant, we should see gamma rays. And we do. And this is an image of the remnant of a supernova explosion in gamma rays. And you see that you see a nice shell here, which is a shock wave expanding. And it means that cosmic rays are indeed accelerated in supernova remnant explosions in the shock following supernova remnant explosion. So basically, I think I should move quickly to my conclusions. So basically now you can consider yourself a cosmic ray physicist because you know all the story, and you can summarize basically what I call orthodoxy, so what most people think about cosmic rays, in 3 main points. First of all, the energy you need to explain cosmic rays comes from supernova explosions. Then the second point is the cosmic rays are confined in the galaxy, not in the galactic disk, but in an extended magnetized galactic halo. And then cosmic rays are accelerated, and you remember that dust must play a role, and we believe that they are accelerated at the shocks that are generated in the interstellar medium after a supernova explodes. And I conclude with this, which is just an image of AMS. AMS is a particle detector which is on the International Space Station, and is a cosmic ray detector. And it operates since 15 years. And in 15 years, he observed, how do I read this number? 260 billion cosmic rays. And that's why we need people able to dig into incredibly large amount of data. And that's all for me.
Okay, thanks, Stefano, for your nice presentation. It's really exciting. If someone from participant has any questions, please. Anyone has a question? Uh, Maybe I have a question, Stefano.
Yes.
Uh, like that, why do different energy ranges of cosmetic rays seem to demand different astrophysics sources? And what does that patchwork tell us about how the universe accelerate practicals?
Yes. Okay, let me go back to, that's a good question. Let me go back to this. Okay, for example, this. So this is basically, you see,
Yeah.
this is the spectrum of cosmic rays. This is the energy of the particle, and this is how many particles, I mean, the flux, basically. And one of the most striking things here is that here is a log scale. So you have 11 orders of magnitude in energy. This is huge. I mean, it's you go from from energy which for our everyday life are very small, but the particles at the end of the spectrum have energies that this is comparable of I mean when Roger Federer does ace, the ball has this energy, so it's a macroscopic energy. Now, of course, you cannot use the same astrophysical object and mechanism to explain these particles and these particles because there is simply no way. So what we believe at the bulk, so basically this here is accelerated in galactic objects such the remnants of supernovae. And these are basically the shock waves that form that can accelerate particles. Then the point is that we don't know exactly up to which energy this object can accelerate particles. What we would love is to go at least up to here, to say that they do all the galactic cosmic rays and then they drop, and then there are other sources that come up here and explain this.
Mhm.
But in fact, we don't know because we do not have evidences. We have evidences of the fact that they accelerate up to this domain here, more like TV domain, but from here on we don't have evidences, and so we are searching for these evidences, building, for example, gamma ray telescopes that are able to observe larger energies, but we don't know. And even from the theoretical point of view, is not easy to accelerate these particles here in the remnants of supernovae. Now, what about the extragalactic, which is something that should pop out here and then explain this? Here we believe that it is most. I mean, we have several candidates. In fact, the situation is much less clear. We have several candidates here. For example, active galaxies or gamma ray bursts, which are like explosions, which are much more energetic than supernova explosions, and much more rare, of course. Or other ideas to explain this are even, let's say, um,
Yeah.
the collisions between large-scale cosmological structure and so on. But the situation here is much less clear than here, because here we know more or less a supernova explosion can do the bulk. Then, of course, here we have some doubts, but here we don't have one candidate which is clearly emerging. So it's much less clear.
Yeah, it's really clear. Yeah. Anyone else has a question? Anyone else?
I have a question.
Yeah.
Many thanks, Professor Stefano. I would like to ask you, the behavior of cosmic rays is constant.
The behavior of cosmic rays is yes, is very, you mean in time, I guess. If you mean in time, yes, it is extremely constant in time. And the reason is that even if these cosmic rays are I produce in supernova, so in impulsive events. So you have to imagine the galaxy, and 3 times per century, boom, you have an explosion, you accelerate cosmic rays, and then boom, boom, boom. So
Yeah.
in the absence of a magnetic field, you would see cosmic rays changing in time. But in fact, the magnetic field is messing up all particle trajectories and is keeping them for a long time so that you reach a steady state. And in the end, what we say is extremely stable in time. And it has to be stable for billions of years. We know now from a number of observables. So it's extremely stable in time.
Yeah. Okay. Anyone else, please?
Yes, Stefano, I would like to ask you. So, is there a certain strength of the magnetic field or the anomalous in the magnetic field that might affect the cosmic rays, or it's something unknown, or it really has a certain value, or?
Now we know, okay, we know very well the strength of the magnetic field in the galaxy is about several micro Gauss. So you have to compare with, I mean, the magnetic field in the Earth is, I think, 1 Gauss, and so it's very small in the interstellar matter, but still is enough to keep particles in. What is much less known, you have to imagine that this magnetic field is very turbulent, so it's not just magnetic field lines are not just nice ordered lines, but are completely turbulent. And so you describe normally turbulent fields in terms of the power spectrum of the magnetic field. So a teach is a superposition of modes of different frequencies, and the power spectrum tells you where the magnetic power is, if it is at large scale, small scale, and so on. And this is something which we know, which I mean, we have measurements of this, but these measurements are quite indirect, and so it's something which is more problematic. And this is important because how the magnetic field energy is splitted into different spatial scales, it is extremely important to study how cosmic ray particles move in these magnetic fields. And so this is in fact one of the studying the motion of cosmic ray particles in turbulent magnetic fields is a mess and is a subject of a lot of investigation. There are a lot of people studying what we call the transport of cosmic rays in turbulent magnetic field. So we know the strength very well, few micro Gauss, but the structure, the topology, it's much more difficult to be determined.
I see. Thank you very much. Thank you
Thank-
for the nice talk very much. It's really interesting. It's very close to my heart because
Okay.
it's a subject. Thank you very much.
Yeah. Anyone else has a question? So by the end, Stefano, I would like again to thank you in behalf of all, in behalf of me, and behalf of Physics Without Frontier member, extra to Hala. It's our pleasure like to have you, and we would like to have you in future events.
Sure.
Thank
Absolutely.
you again, and have a good evening. All.
You too. Thanks a lot, and bye-bye.